Welcome back to Physics 192. I'm Gerard Blanchard. Last time we introduced equivalent resistance of a circuit, so let's do an example to practice that. Find the equivalent resistance between terminals A and B to replace all of the resistors in this circuit. Okay, let's draw this circuit. Here's our battery with 6 volts positive. Actually, that's not going to really matter. Here's point A, and here's point B, and there's a resistor connecting points A and B directly, and that has 4 ohms. And then we have a 2 ohm resistor here, and a 4 ohm resistor connecting that to point B. And then we have another 2 ohm resistor, and then a 4 ohm resistor, and then a 4 ohm resistor connecting along the diagonal. And let's see, 2, 2, 4, 4, 4, 4. Okay, we've drawn the diagram. We have to start looking for resistors that are in parallel or in series. And what I see here is between B and this point here, between this point and this point, we have 2 resistors that are in parallel, meaning that the current can go from here to here or from here to here and cross only one resistor along each path. So these 2 resistors are in parallel, so we can combine them into a single resistor. So let me draw the diagram quickly before we calculate what that is. Okay. And we're going to combine them into a single resistor. Connecting point B. So that's our 4, 4, 2, and 2. And we'll call this RE1, where 1 over RE1 is equal to 1 over 4 plus 1 over 4, or 1 over RE1 is equal to 1 over 2, or RE1 is equal to 2, so RE1 is a 2 ohm resistor. Now, along this path, I see that this resistor and this resistor are in series. So we can combine those into a single resistor, and I guess I'll go down this way. Combine those into a single resistor, redraw my circuit. Two, 4, 4, and now these 2 resistors we're going to combine into a single resistor, call it RE2. Oops, I'm sorry, that's not RE2. This would be RE2, because this is our 4 ohm resistor right here, and these 2 are being combined into another resistor that's down here. And RE2 is equal to 2 plus 2, or RE2 is equal to 4. So RE2 is equal to 4. And now you can see that between this point and this point, I can go either along this path or along this path and cross only one resistor at a time. And you see that we have two 4 ohm resistors in parallel. And we already worked that out. When you have two 4 ohm resistors in parallel, they give you an equivalent resistance of 2 ohms. So I'll go ahead and draw my next circuit. And this makes a 2. And I still have this resistor right here, which is a 4 ohm resistor. And as you can see, we have two 2 ohm resistors in series. And so 2 plus 2 is going to give us 4. So I'll go this way now. And we have our battery. And we have, oops, there's a resistor right here. We have a 4 and a 4. And remember that this is point B and this is point A. And you can see that from point B to point A, we have a 4 ohm resistor in parallel with a 4 ohm resistor, and which we already worked out. So we know that two 4 ohm resistors in parallel are going to give us a 2 ohm resistor. So this whole circuit, or the initial circuit right here, is equivalent to a single 2 ohm resistor between A and B. There's A, and there's B, and a 2 ohm resistor. I should say that this whole circuit is equivalent to a 2 ohm resistor as far as the battery is concerned. So that's how we go about combining parallel and series resistors into equivalent resistors. And remember, 2 resistors are in series if the current must flow through one and then through the other. Just like we had right here, where the current, whatever current flows through this resistor must flow through this resistor. And resistors are in parallel whenever there are 2 paths between a pair of points and there's only one resistor along each path. And then we can use our equations for combining resistors. If the resistors are in parallel, then it's 1 over the equivalent resistance is 1 over resistance 1 plus 1 over resistance 2. And if the resistors are in series, then the equivalent resistance is simply the resistance of resistor 1 plus the resistance of resistor 2. So far we've been talking about electrical circuits using only batteries, resistors, and conductors. And in those circuits, whatever current flows in them is constant in time. The reason for that is that the current through and the voltage across a resistor can change essentially instantaneously, meaning within a few nanoseconds, from one constant level to another constant level. However, when we introduce inductors and capacitors into a circuit, the voltage and current become time dependent. What is an inductor? An inductor is also known as a coil, meaning a coil of wire, and the symbol for an inductor is simply a symbolic coil of wire, as you can see here. The voltage difference across an inductor is equal to the inductance, L, of the inductor times the change in current divided by the change in time. Inductance is measured in units of henries, where a henry is a volt times a second divided by an ampere, and the voltage drops in the direction of current if the current is increasing, and the voltage increases in the direction of current if the current is decreasing. the voltage change is 0 if the current is steady. If the change in current divided by the change in time is 0, then the voltage difference across the inductor is also 0. And finally, unlike resistors, inductors do not dissipate power. Instead, they store energy. And the energy stored in an inductor, capital U, is equal to 1/2 of the inductance times the current through the inductor squared. Now, the physics behind an inductor is electromagnetic induction, as we talked about at the end of our first section of this course. The electromotive force in an inductor is equal to the change in magnetic flux in the inductor divided by the change in time. You'll remember that rule for magnetic induction. When the magnetic flux through a loop or a coil changes, then there is an EMF generated, and the EMF is equal to the change in magnetic flux divided by the change in time. The magnetic flux through the loop is equal to the self-inductance times the change in current through the loop. That's something that we calculated at the end of the first part of this course. And that is what gives rise to the relationship that the change in voltage across an inductor is equal to the inductance times the change in current divided by the change in time. Basically, what's going on here is that when there is a current through a coil, the coil generates a magnetic field through itself and a magnetic flux through itself. Then, if we try to change the current, the induced electromotive force drives a current that resists the change. So if there is a current through an inductor, the current, any change will be resisted. Either an increase or a decrease in the current will be resisted. And that is what gives rise to our rule that the change in voltage across an inductor is equal to the inductance L times the change in current divided by the change in time. How do we deal with circuits containing inductors? Well, if the change in voltage depends on the change in current divided by the change in time, you can see that we're dealing with a time interval. We have an initial time and a final time. What you do is you use Kirchhoff's laws to calculate the initial current from the initial circuit and the final current from the final circuit. Then we calculate what is called the time constant. And the time constant is represented by a lowercase Greek tau. That little t is actually a tau. And the units of tau, the units of the time constant, are seconds, units of time. And we calculate the time constant from the final circuit. And the time constant depends on two things. It depends on the inductance of the inductor and the equivalent resistance of all the resistors in the final circuit. And the dependence is that the time constant is equal to the inductance divided by the equivalent resistance. So inductance in henries divided by equivalent resistance in ohms gives us a time constant in seconds. Just remember that if you're using your basic metric units, you will get basic metric units out. Then, the current or the voltage in between the start and final time are given by these equations. The current at any time between t initial and t final is equal to the final current plus the quantity initial current minus final current times e raised to the t time divided by the time constant. So that's the exponential function, e raised to the, minus t divided by tau. So I equals I final plus the quantity I initial minus I final times e to the minus t divided by tau. Let's make sure that this works for I initial and I final. For the initial time, t is 0. E to the minus 0 is 1. E to the 0 is 1. And so for t is equal to 0, we have I final plus I initial minus I final, or I is equal to I initial. When time is infinite, then we have e to the minus infinity, and so we would have, which is 0, so we would have I final plus 0. So initially, for t is equal to 0, the current is equal to I initial, and finally, at t is equal to infinity, the current is equal to I final. And so that is our current everywhere in between. The change in voltage in the circuit we can get from the voltage change of the resistors, where the change in voltage is equal to the absolute value of R times I, or R equivalent times I initial minus I final times e to the minus t over tau. And what that means is that when t is equal to 0, then the change in voltage across the inductor is equal to the equivalent resistance times I initial minus I final. And then when t is equal to infinity, the change in voltage across the inductor is 0. Now, if we were given the currents or the voltage across the inductor, and we wanted to know the time at which the current had a particular value, then we would invert these two equations as follows. To invert the current equation, that would be t is equal to tau times the natural log of I initial minus I final divided by the quantity I minus I final. Or t is equal to tau times the natural log of I initial minus I final divided by I minus I final. And to invert the voltage equation, that would be the time is equal to tau times the natural log of the equivalent resistance times the current initial minus current final over the change in voltage. Now remember that current initial is the current at t is equal to 0, and current final is the current after a very long time has passed, or an infinite amount of time has passed. Let's do an example of that to show you that these equations work. Here I have 3 circuits. Let's start with the first one. This circuit contains simply a battery and a resistor, a 1.5 volt battery and a 10 ohm resistor, and a switch. Right now the switch is open, so there's no current flowing at all. We don't have a circuit. And note that I've marked the position at which the voltage is 0. So this is our ground right here where I've marked 0 volts. Now, when I close the switch, current will start to flow, and we can see the current in the resistor in this circuit right here. So this would be current versus time, and voltage across the resistor versus time. So when I close the switch, as soon as I close the switch, the voltage across the resistor jumps up and the current jumps up. So this is the closing of the switch and the current is constant. If I were to close the switch, then the voltage would go off and the current would be a constant 0. I can open the switch, close the switch, open the switch, and so on. And the current changes from either 0 to V divided by R. 1.5 volts divided by 10 ohms is going to give us 0.15 amperes, which is 150 milliamperes. The the reading here is in milliamperes, so this is 150 milliamperes. So as soon as I close the switch or open the switch, the current changes and it stays constant. I close the switch, it changes to 0 and it stays constant. I open the switch and it goes back to 150 milliamperes or 1.5 amperes and stays constant. So with a battery and a resistor, the current changes effectively instantaneously and stays constant. Next, let's take a look at this circuit right here, where I have the same thing. I have a 1.5 volt battery, I have a 10 ohm resistor, but now I've added in a 100 Henry inductor. Okay, let me move my probes that tell the computer where I want to measure the voltage and the current. Okay, so I'm measuring the voltage across the inductor. Let me stop that. Let me erase these graphs. There we go. Okay, so what do we have here? Well, initially, with the switch open, there's no circuit at all, so we have no current flowing. So there's no current flowing, so the I initial will be 0. So the initial current will be 0. Now once I close the switch, imagine that I close this switch, and we'll imagine that a long time passes so that the current has become steady. Once a long time passes that the current is steady, then the voltage change across the inductor is 0, because the change in current divided by the change in time will be 0. So after a long time, the inductor is essentially just a conductor, and we have a 1.5 volt battery and a 10 ohm resistor. So the final current will be 0.15 amperes or 150 milliamperes. So I initial we predict will be 0. I final will be 150 milliamperes or 0.15 amperes. So let's see what happens when I close the switch. I close the switch, and you can see that the current indeed starts at 0 and it changes with time. It's rising. Also note that it is rising initially fast, but it's leveling off. It's leveling off as it heads to 150 milliamperes. So it is some kind of exponential curve. The voltage, in fact, looks a lot more like an exponential curve. It starts up here and it decays exponentially to 0. The current is exponentially approaching 150 milliamperes. So there you see that the current starts from 0, because we said there was 0 current to begin with, because there was nothing flowing in the circuit. But over time, the current will approach 150 milliamperes, and that's what it's doing. It's getting exponentially closer to 150 milliamperes. Let's check our equations. Let me write over here, I initial is equal to 0. I final is equal to 0.15 amperes. R equivalent. Well, there's only one resistor in this circuit, and that is 10 ohms. So R equivalent is equal to 10 ohms. And we also have to calculate our time constant. Tau is equal to the inductance divided by R equivalent, and that is equal to, our inductance is 100 henries, So let me write that as well. L is 100 henries. So tau is 100 divided by 10, or tau is equal to 10 seconds. So our time constant is 10 seconds. So let's see. Let's predict what the current will be at t is equal to 15 seconds. At t is equal to 15 seconds, the current, I, is equal to I final plus I initial minus I final times e to the minus t over tau, or the current, is equal to I final, which is 0.15 amperes, times I initial, which is plus 0 minus 1.5 amperes, times e to the minus t. We're going to say t is equal to 15 seconds divided by tau of 10. And so what is that? Let me simplify that a little bit. I is equal to 0.15 minus, this is not 1.5. This is also 0.15. There we go. This I final, 0.15. So 0.15 minus 0.15 times e to the minus 15 over 10. And let's see what that is equal to. 0.15 minus 0.15 times e raised to the minus 15 divided by 10. And that predicts that at t is equal to 15 seconds, and let me make a note of that. This is t is equal to 15 seconds, that the current is equal to 0.117 amperes, or I is equal to 117 milliamperes. So let's take a look at our graph. Here is t is equal to 15 seconds. We'll follow that up. And right here is the current at that time. And the current at that time is almost 120 milliamperes. It's a little bit less, so 117 milliamperes sounds good. So we have successfully predicted the current through that inductor at that time. How about the voltage? The voltage, at t is equal to 15 seconds? Delta V is equal to the absolute value of R equivalent times I initial minus I final times e to the minus t over tau, or delta V is equal to R equivalent is 10 times 0 minus 0.15, close my absolute values there, times e to the minus 15 for t divided by 10 for tau, or delta V is equal to the absolute value of negative 1.5 e to the minus 15 over 10, or delta V is equal to 1.5 e to the minus 15 over 10, or delta V is equal to 1.5 times e raised to the minus 15 seconds divided by 10 seconds. And so that would predict that delta V across the inductor is equal to 0.335 volts at t is equal to 15 seconds. So let's take a look at our graph over here. And here we have 15 seconds, and the this line, this is 0 and this is 0.6. So the, yeah, I would say that 3.35 is pretty good for that. It's more than halfway. Halfway would be 3, but it's only a little bit more than halfway. So 0.335 would be good. So we can predict the voltage and the current at any time by examining that circuit. Now this circuit that I've built here has a flaw. Now that we have a current flowing through the circuit, the inductor will resist any change in the current. Let's think about what's going to happen if I open that circuit, if I open the switch. Well, there is a current flowing through the circuit of 0.15 amperes, and the inductor will keep that current going even after I open the switch. Let me open the switch, and you see we have a big spark, and in a very dramatic fashion we've burned out our switch. Take a look at the voltage over here. The voltage spiked negatively, very large negative spike in the voltage. The voltage is negative because the current was decreasing. Remember that the voltage increases in the direction of the current if the current is decreasing, which means that over here, if this is 0 and we're over here and the voltage is increasing in this direction, then it must be negative here. So the voltage is negative because the current's decreasing, and the voltage is a very large negative because we were trying to change the current over a very short time. So L times the change in the current over the change in time was very big. So we had a very large voltage, which caused a spark, and it caused that switch to burn out. You may have experienced this yourself if, for example, you tried to unplug a vacuum cleaner that's running. The motor of a vacuum cleaner is made up of a coil of wire around a magnet, and so the motor has in itself a large inductance. So if you try to unplug it suddenly, then you might see a spark from trying to decrease the current too quickly. You might see this in other cases if you unplug a power tool too quickly. So that's what's going on here. The motor has a large inductance and it resists a large change in current, so it can actually create a high enough voltage to drive a current through the air, which we call a spark. So it makes a big spark, which also can cause damage. So to avoid that kind of damage, I have my third circuit over here. Let me take my probes and put them over here. And what I've done here is I have added another resistor. I still have my battery. The battery is the same. This resistor is the same. The inductor is the same. But now I've added this resistor right here. And that way, now when I close the circuit, we see the current increasing as normal because this battery is driving a current through this resistor and this inductor. So we have the same circuit as we did over here as far as the inductor is concerned. Now as far as the battery is concerned, it's also driving another current across this resistor, but that's okay. What happens now when I open the circuit is that this current, you see that we have a current flowing through this inductor like this. That current will still flow, but since it can't flow through the switch, since it can't flow in this sense, it will go through this resistor, and you'll see the current in this resistor change signs. There's some really tiny little arrows here. And if you can see those arrows, you'll see them reverse as soon as I open the switch. Okay, so now the current is flowing up through this resistor. So now we have a current flowing like this. So the current that was initially flowing through the inductor is decaying away exponentially. So now our new circuit is like this. And it's in fact the inductor that's driving this current through this circuit. It's driving a voltage that is pushing a current through these two resistors. And the reason why it's doing that is because there was a current initially, and the inductor resists a change in the current. So if at all possible, the current will keep flowing, and it will flow through these resistors, but as the energy that was stored in the inductor is dissipated, the current and the voltage will both approach zero exponentially. In this circuit, I can close the switch, open the switch, close the switch, open the switch, and nothing dramatic happens. Let's work one example to give you some practice working with inductors. No currents flow in this circuit before the switch is closed. Consider all of the circuit elements to be ideal. Ideal resistors, ideal inductors, and an ideal battery. The first question is, at the instant that the switch is closed, what are the values of the currents I1 and I2? Secondly, after the switch has been closed for a long time, essentially an infinite time, what are the values of the currents I1 and I2? Now remember a couple of things. The first is that the current through an inductor does not change instantaneously. And the second thing is that once a current has been flowing through an inductor for a long time and it becomes constant, the change in voltage across the inductor is zero, and the inductor acts effectively like a conductor. Okay, let's draw our diagram. Here's our 45 volt battery. Here's our switch. We have a 3 kilo ohm or a 3000 ohm resistor, an inductor, which is a 15 millihenry, which is, I'll multiply that by 1 Henry over 1,000 millihenries, and that would be 0.015 henries. And we'll close that circuit there. And we have a 27 kilo ohm or 27,000, sorry. 27 kilo ohm is 27,000 ohm resistor. And I1 flows this way, and I2 flows that way. And initially, the switch is open. So we will close the switch. So when we close the switch at t is equal to 0, when we close the switch at t is equal to 0, we have for this loop, for the loop where we go across the battery and across this resistor in the direction of I1, we have delta V total is equal to 0, which tells us that plus 45 minus 27,000 I1 is equal to 0. because all we have here is a resistor. As soon as we close the switch, effectively instantaneously, current, the full constant current flows through this resistor, and then we're back to 0. So that tells us that 45 is equal to 27,000 I1, or 45 divided by 27,000 is equal to I1. And what is that? 45 divided by 27,000, that's equal to 1.67 times 10 to the minus 3 amperes, or 1.67 milliamperes, is I1. Okay. How about in this direction? Okay. Through this loop. Well, at the moment, or immediately before the switch is closed, there was no current flowing over here. That's what we were told. So if there's no current flowing over here, then at the moment that the switch is closed, then there's 0 current here, and it will stay 0 current. So since before the switch was closed, there was no current flowing in this inductor, the inductor will keep the current from changing instantaneously. So, and let's see, let's call this I1 initial. So I1 initial is that I2 initial is equal to 0. And we figure that out because it was 0. And so when we close the switch, it does not change instantaneously. So the initial current over here is 0. How about after a very long time? Okay. So actually I'll do that over here. T, we'll call it t is equal to infinity. After a very long time, well, after a very long time, nothing has changed over here. Okay, in this circuit, nothing has changed. We still have 45 volts and 27,000 times I1. So I1 final is the same as it was before, 1.67 times 10 to the minus 3 amperes. So the current across I1 never changes. How about I2? After a very long time, the current through this loop has stabilized. It's reached whatever value it's going to reach, and it's not going to change anymore. When the current is no longer changing across the inductor, the voltage drop across the inductor is 0, and the inductor is essentially a conductor. The inductor is essentially a conductor. So for this loop, we have plus 45, or delta V total is equal to 0, which would be 45, and then minus 3,000 I2 final. And then as we go across the inductor, that's 0. So no change across the inductor. So I'm going to write plus 0. No change across the inductor because time has gone on and the current has stabilized again. So no voltage drop across here, and we're back to where we started. That's equal to 0. That says that 45 is equal to 3,000 I2 final, or 45 divided by 3,000 is equal to I2 final. And what is that? 45 divided by 3,000 is equal to 0.015 amperes is equal to I2 final. So the final current through this part of the circuit is exactly what we would get if the inductor weren't there, or 0.15 amperes. So the current through this resistor instantaneously jumps up to 1.67 times 10 to the minus 3 amperes, and it stays like that forever. When the switch is closed, there's zero current over here, and it stays zero initially, but it eventually will exponentially approach 0.015 amperes at t is equal to infinity, or after a very long time. We'll work with inductors some more next time. Until then, think physics.